Black holes are frequently pictured as cosmic vacuum cleaners, aggressively slurping up every star, planet, and speck of dust in their neighborhood. But if you replaced our sun with a black hole of equal mass, Earth would keep orbiting exactly as it does now. There is no active pulling force uniquely sweeping through the cosmos. The actual boundary of a black hole, the event horizon, doesn't have a crust you can crash into. It is a strictly mathematical line drawn across the fabric of spacetime. But cross that invisible threshold, and you have reached the ultimate point of no return. The strange thing about this boundary is how it completely fractures our concept of experience. The laws of physics warp so severely here that watching someone cross the event horizon and crossing it yourself produce two wildly contradictory versions of reality. To actually understand what happens at the edge of a black hole, we have to throw out the idea of a single shared universe and explore both of these distinct perspectives. On Earth, breaking free requires roughly 11 kilometers per second. Compress that mass into denser space, and escape velocity shoots up. Shrink it until escape velocity surpasses 300,000 kilometers per second. That exact mathematical distance is the Schwarzschild radius. Since the laws of physics dictate that absolutely nothing in the universe can travel faster than the speed of light, anything that slips inside this specific radius is permanently trapped. The event horizon, then, is a universal speed limit problem taken to an absolute mathematical extreme. Let's step back and imagine you are a safe distance away, safely watching an object fall toward that trap. According to general relativity, extreme gravity literally bends and stretches time, a concept known as time dilation. Because of this warping, as you watch the object get closer to the horizon, its clock ticks slower relative to yours. From your vantage point, the falling object slows down exponentially, eventually appearing to freeze completely right at the edge. As that frozen image sits there, the light it emits has to constantly fight against the immense gravity well to reach your eyes. This struggle stretches the light waves out, shifting them toward the red end of the spectrum, a process called gravitational redshift, causing the frozen image to slowly fade into darkness. To the rest of the outside universe, falling objects never actually cross the event horizon. They simply become frozen, fading ghosts plastered permanently against the boundary. The reality for the traveler falling inward is completely different. They do not experience any freezing or slowing of time on their descent. Because the event horizon is a mathematical line in space rather than a physical wall, the traveler would pass right through it, potentially without even noticing the exact moment they left the observable universe behind. If the black hole is small, the traveler experiences intense tidal force